In 2024, astronomers staring at the supermassive black hole at the center of our galaxy detected something that should not have been possible. Light from a single flare, a brief outburst of energy on the inner edge of the accretion disk, arrived at their instruments not once but twice, then a third time. The same flare, the same moment of cosmic violence, recorded at the same telescope but separated by intervals of minutes. The light had traveled the same distance through the same space. The only difference was that some of those photons had taken a longer path around the black hole before escaping, and in that longer path time had passed differently. Not for the photons. For the moment itself. Researchers were watching the same event unfold at different speeds in the same sky. For nearly a century, physicists have known that time near a black hole runs slower than time far from it. The equations have predicted it since 1915. Atomic clocks on aircraft have confirmed it. GPS satellites in orbit have to be corrected for it every single day, or your phone would not be able to find a coffee shop. But the question that has haunted physics for 100 years is not whether time slows down near a black hole. It is why. What is actually happening to time when it gets close to one of these objects? Is time being stretched? Is it being absorbed? Is it being canceled? And in the last few years, working with data from the Event Horizon Telescope, from gravitational wave observatories, and from a new generation of theoretical models, scientists have begun to converge on an answer. An answer that does not just explain why clocks run slow near black holes, it rewrites what time actually is. Tonight we are going to follow that answer all the way down. We are going to start at the edge of the event horizon, and we are going to descend toward the singularity. We are going to meet the equations that predicted all of this before any telescope was powerful enough to test them. We are going to walk through the experiments that confirm time itself is not a fixed quantity, but a property of space that can be deformed, stretched, and in the most extreme cases broken entirely. We are going to confront the photograph that the Event Horizon Telescope released in 2022 and understand for the first time what it is actually showing us. We are going to follow a hypothetical astronaut as they fall toward an event horizon, and we are going to feel what they would feel, see what they would see, and lose what they would lose. And by the end, we will not just understand why time slows down near a black hole. We will understand that the answer is far stranger than anyone expected. Because time does not slow down near a black hole. Time is what a black hole is made of. If you enjoy these nighttime journeys into the deep questions of physics, please take a moment to like and subscribe. It helps the channel reach more curious minds, and it lets us keep building these documentaries for you. Now let us begin. The first thing to understand is that time was never what you thought it was. For most of human history, time has been treated as a backdrop, a stage on which events unfold. The play is the universe. The actors are matter and energy. Time is the silent author of the script who never appears on stage. It passes uniformly, indifferently. The same in every theater, on every street, in every city. A second in your kitchen is a second on the moon, is a second on a passing comet, is a second in the heart of a distant star. That was the assumption that built the modern world. Isaac Newton wrote it into the foundation of physics in 1687. In his Principia, the most influential book in the history of science, Newton declared that absolute true and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Equably, the word means uniformly, evenly, smoothly. Time, in Newton's universe, was a single river flowing in one direction, the same width and depth and speed everywhere. Every clock in existence was measuring the same flow, just with different instruments. If one clock disagreed with another, one of them was broken. For 228 years, that assumption held. It was the bedrock of mechanics, of astronomy, of engineering, of every scientific discipline that touched motion. It was also wrong. The first crack appeared in 1905 when a young patent clerk in Bern, Switzerland, published a paper titled On the Electrodynamics of Moving Bodies. The clerk was Albert Einstein. The paper introduced what would later be called special relativity, and it carried within it a result so strange that even Einstein himself spent years trying to fully reconcile with its implications. The result was this: time does not flow at the same rate for all observers. If two people are moving relative to each other, their clocks disagree. Not because the clocks are broken, because time itself is different for them. This was not a small correction, this was not a rounding error. This was a structural revision of what time is. Einstein showed that the faster you move through space, the slower you move through time, as measured by someone watching you from outside. A clock on a fast-moving train ticks more slowly than a clock at the station, not because the train's mechanism is affected by motion, but because time itself is dilated, stretched, made longer. From your perspective inside the train, everything feels normal. Your heart beats at its usual rate. Your watch ticks once per second. You age at your usual pace. But to someone standing on the platform watching you go by, your watch is ticking more slowly than theirs. Your heart is beating more slowly. You are aging more slowly. Both observers are correct. There is no privileged frame of reference. Time is not a single river. It is 1,000 rivers, each one flowing at the speed of whoever is watching it. This was 1905. It was already shocking. But Einstein was not done. Special relativity dealt only with observers moving at constant velocity in straight lines. It did not handle acceleration. It did not handle gravity. For 10 more years, Einstein worked to extend his theory to include those forces. The result, published in 1915, was general relativity. And it took the strangeness of special relativity and made it cosmic. General relativity stated that gravity is not a force in the traditional sense. It is a property of geometry. Mass and energy curve the fabric of space-time, and objects moving through that curved geometry follow what appear to be curved paths. A planet orbiting a star is not being pulled by an invisible force. It is moving in a straight line through space that has been bent by the star's mass. The orbit is the shape of the bend. But here is where general relativity went farther than anyone expected. Einstein realized that if mass curves space, it must also curve time. Space-time is not two separate things. It is one four-dimensional fabric. Mass affects all of it. A heavy object does not just bend space around itself, it bends time around itself. Time passes more slowly in the presence of mass. The closer you are to a mass, the slower your clock runs. This is called gravitational time dilation. It is a direct prediction of general relativity. And in the equations, it is not an exotic effect requiring extreme conditions. It happens everywhere. Right now, the clock on your wrist is running slightly slower than a clock in orbit, because you are deeper in Earth's gravitational well than a satellite. Your head is aging slightly faster than your feet, because your head is slightly farther from the center of Earth's mass. The difference is measured in nanoseconds per year, but it is real. It has been confirmed in laboratories using atomic clocks separated by less than a meter of altitude. The clock that is higher ticks faster. The clock that is lower ticks slower. Time is not flowing equably. Newton was wrong. Einstein was right. And the strangeness only deepens when you consider what happens when the mass becomes extreme. Chapter 1. The geometry of falling. Gravitational time dilation is gentle on Earth. The effect on a wristwatch from being at sea level rather than on top of Mount Everest is roughly a few microseconds per year, detectable with sensitive instruments but invisible to daily life. Even on the surface of the Sun, the effect is modest. Clocks tick about 2 parts per million slower than clocks at the radius of Earth's orbit. Noticeable, but not extreme. But gravity does not stop scaling. The more mass you concentrate in a small enough space, the deeper the gravitational well becomes. And the deeper the well, the more time slows. There is a specific moment in the mathematics, a specific point in the equation, where gravitational time dilation goes from significant to catastrophic, where time does not just slow down, it stops. That point has a name. It is called the Schwarzschild radius. And the object that fits inside it is what we call a black hole. The Schwarzschild radius was discovered in 1916, just months after Einstein published the field equations of general relativity. A German physicist named Karl Schwarzschild was serving in the German army on the Russian front during the First World War. He was suffering from a rare and painful skin disease that would kill him within the year, and he was reading Einstein's papers. From a trench, from a field hospital, in conditions of misery that are difficult to imagine, Schwarzschild solved Einstein's equations for the simplest possible case: the spacetime around a perfectly spherical, non-rotating, uncharged mass. He sent his solution to Einstein in a letter. Einstein responded with astonishment. He had not expected an exact solution to exist. He had not expected it to be found so quickly. He had not expected it to come from a soldier writing equations between artillery barrages. Schwarzschild's solution described how space and time curve around a concentrated mass, and it contained a feature that nobody at the time could quite believe. If you compressed the mass into a small enough sphere, the curvature became infinite. The equations broke. Time stopped. Schwarzschild calculated the critical radius for this to happen. For an object the mass of the Sun, it was about 3 kilometers. For an object the mass of Earth, it was about 9 millimeters. Compress the Sun into a ball 3 kilometers across, and the geometry of space-time around it would do something the universe had never been observed to do. It would create a one-way door, a boundary beyond which nothing could escape. Not light, not information, not time itself. For decades, this was considered a mathematical curiosity. Einstein himself doubted that such objects could exist in nature. He published a paper in 1939 trying to prove that no physical process could ever compress matter to the Schwarzschild density. He was wrong. By the 1960s, observations of intense X-ray sources, of unusually fast-moving stars near the centers of galaxies, of objects that emitted enormous amounts of energy from tiny regions of space, all began to point to the same conclusion. Black holes are real. They exist. The universe is full of them. And inside the Schwarzschild radius, the equations were telling us something even stranger than anyone had been willing to accept. Chapter 2. The Frozen Star. Here is what gravitational time dilation looks like when you push it to its extreme. Imagine you are floating in space at a safe distance from a stellar mass black hole. The black hole is about 3 times the mass of the Sun. Its Schwarzschild radius, the boundary we call the event horizon, is about 9 kilometers across. The black hole has a partner, a friend who has volunteered for an experiment. The friend straps on a powerful rocket and a clock and begins to descend toward the black hole. They are wearing a beacon that emits a steady pulse of light, 1 flash per second, by their own clock. You are going to watch what happens to that beacon as your friend falls. At first, everything looks normal. The friend descends slowly. The flashes arrive at your eyes at a rate of 1 per second, just as the friend's clock is ticking. As the friend gets closer to the black hole, however, you notice something. The flashes are starting to slow down, not by much at first. A flash every 1.1 seconds, then 1.2 seconds, then 1.5 seconds. From your perspective, the friend's clock is running slow. From the friend's perspective, nothing is happening. They look at their watch. It is ticking once per second. Their heart is beating normally. They feel fine. The flashes leave the beacon at the same rate they always have. But the gravitational well between the friend and you is deepening, and that well is stretching time. The light from each flash has to climb out of a steeper and steeper slope to reach you. And as the light climbs, the time between flashes stretches. The friend continues to descend. The flashes continue to slow, a flash every 2 seconds, a flash every 5 seconds, a flash every minute. The light is also getting redder. The same gravitational pull that stretches time also stretches the wavelength of the light. Blue light becomes red, red becomes infrared, infrared becomes microwave. The friend, from your point of view, is becoming dimmer and slower. As the friend approaches the event horizon, the effect becomes extreme. The flashes are now coming hours apart, then days, then years. The friend appears, from your perspective, to be slowing down so dramatically that they will never actually reach the horizon. They will hover above it forever, getting redder and dimmer and slower, asymptotically approaching the boundary but never crossing it. This is why black holes were once called frozen stars. From the outside, anything falling toward the event horizon appears to slow down and freeze. The image of the infalling object stretches into infinity. The light from that final moment of approach gets red-shifted into oblivion. The friend, in your eyes, becomes a stationary smear of fading red light hanging just above the boundary. They never fall in, they never disappear, they just fade. But from your friend's perspective, the experience is completely different. Their clock continues to tick normally. They reach the event horizon in finite time, by their own watch. They cross it. In fact, if the black hole is large enough, they cross the event horizon without noticing anything at all. There is no wall. There is no boundary they can feel. The horizon is not a physical object. It is a mathematical surface, a point of no return defined by the geometry of spacetime, not by any local feature of the universe. The friend falls through it smoothly. And after that, the inside. We will return to what happens after the friend crosses the horizon. We will follow them down. But first, we need to understand why this is happening. We need to understand the actual mechanism. We have just described the effect of gravitational time dilation in its most extreme form. We have not yet explained why it occurs, and the explanation is the part that has been refined the most dramatically in recent years. Chapter 3. What gravity actually is. The simplest answer to why time slows near a black hole is the textbook answer. Gravity bends space-time. Mass curves the geometry. Time is part of the geometry. Therefore, time gets bent too. This is true. It is what the equations of general relativity say. But it is also, in a sense, a description rather than an explanation. It tells us what happens. It does not tell us why. For most of the 20th century, that was as far as physics could go. Einstein's field equations described the curvature of space-time in the presence of mass and energy. They produced predictions that agreed with every experiment ever performed. But the equations themselves did not say what space-time is. They treated it as a smooth four-dimensional manifold, a kind of mathematical fabric whose shape can be calculated. They did not explain why mass curves it, or what the fabric is made of, or where time comes from. In the last 20 years, that situation has begun to change. Researchers working in quantum gravity and string theory and loop quantum gravity, and in a relatively new framework called entropic gravity, have started to converge on an idea that is reframing the question. The idea, in its simplest form, is this. Spacetime is not fundamental. It is emergent. It is built out of something deeper, and that something has to do with information, with entropy, with the way quantum states are entangled with each other across what we perceive as distance. To unpack what this means, consider a comparison. Temperature is not a fundamental property of matter. Temperature is the average kinetic energy of the molecules in a substance. Hot water is just water with fast-moving molecules. Cold water is water with slow-moving molecules. Temperature is real, but it is built out of motion. It emerges from the collective behavior of trillions of microscopic objects. A single molecule does not have a temperature. Only collections of them do. Researchers in quantum gravity are now proposing that space-time works similarly. The fabric of space and time, the smooth four-dimensional geometry that Einstein described, may not be fundamental. It may be an emergent property of something deeper. The underlying reality may be a network of quantum information, of entangled states, of microscopic degrees of freedom that we cannot directly observe. And what we perceive as space and time may be the macroscopic average of those microscopic states. If this is correct, then mass does not literally bend a fabric. Mass concentrates information. Mass disturbs the quantum substrate. And what we experience as gravitational time dilation is the response of that substrate to having information packed into a small region. The 2010 paper by Erik Verlinde, a physicist at the University of Amsterdam, was one of the first to make this argument in a precise form. Verlinde proposed that gravity is an entropic force, a force that emerges from the statistical tendency of systems to move toward higher entropy. In his framework, what we call gravitational attraction is the universe's response to differences in information density. Where information is concentrated, time slows. Where information is spread thin, time runs fast. Verlinde's specific model has been debated, refined, criticized, and partially superseded by other approaches in the years since. But the core insight, that gravity and time dilation may be reflections of something happening at the level of quantum information, has only grown stronger. The breakthrough came from a surprising direction, from black holes themselves. In 1973, Jacob Bekenstein at Princeton proposed that black holes have entropy, and that the entropy is proportional to the area of the event horizon. In 1974, Stephen Hawking proved that black holes radiate. They are not perfectly black. They emit a faint glow of thermal radiation, now called Hawking radiation, and that radiation carries information about the black hole's temperature and entropy. Together, these results revealed something extraordinary. The entropy of a black hole, the amount of information it contains, is proportional to the area of its boundary, not its volume. In a normal three-dimensional object like a cup of coffee or a planet, the entropy scales with the volume. More states, more entropy. But for a black hole, the entropy scales with the surface. This is called the holographic principle, and it implies that all the information about what is inside a black hole, every particle, every quantum state, every piece of history, can be encoded on the two-dimensional surface of the event horizon. The interior is in some sense a projection, a hologram, a construction built up out of degrees of freedom that live on the boundary. If the holographic principle is correct, and decades of subsequent work in string theory and theoretical physics suggest that it is, then space-time itself behaves like a hologram. The three dimensions of space we see around us, plus the dimension of time, may all be projections from a lower dimensional information layer. And the way mass curves space-time, the way time slows in a gravitational field, may be the projection's response to having information piled up in one location. When you stand on Earth's surface, you are sitting on top of a tremendous amount of mass energy. That mass energy has entropy, it contains information. And the way the local geometry of space-time adjusts to the presence of all that information is what you experience as gravity, and what your clock experiences as time dilation. Near a black hole, the effect is taken to its limit. A black hole packs the maximum possible information into the smallest possible region. It saturates the bound that Bekenstein discovered. There is no denser configuration of information allowed by the laws of physics. At the event horizon, the geometry of spacetime has been pushed to the absolute extreme of what curvature can accomplish. Time, as measured by an external observer, stops, because the information density at the boundary has reached the ceiling. There is nothing more it can do. This is the answer that has been emerging in the last 20 years, and that recent observations have begun to support. Time does not slow near a black hole because the gravitational field is strong. Time slows near a black hole because gravity is what information density looks like from the outside. And at the event horizon, you have hit the maximum. Chapter 4. The photograph that proved it. On April 10, 2019, a global collaboration of more than 200 scientists released an image that changed astronomy. It was the first photograph ever taken of a black hole. The object was Messier 87 star, the supermassive black hole at the center of the galaxy M87, 55 million light-years from Earth. The black hole has a mass of approximately 6.5 billion suns. The image showed a glowing orange ring with a dark circle at its center, a shadow where light fell into the event horizon and never returned. The image was not a single photograph from a single telescope. It was a composite assembled from data collected by an array of radio telescopes scattered around the world, working together as if they formed a single instrument the size of the planet. The project was called the Event Horizon Telescope. It had been in development for more than a decade, and the image it produced was the first direct visual evidence that the predictions of general relativity hold even at the most extreme scales the universe contains. 3 years later, in May 2022, the same collaboration released a second image. This one was of Sagittarius A star, the supermassive black hole at the center of our own galaxy, a mere 26,000 light-years from Earth. Sagittarius A star is much smaller than M87 star, about 4 million solar masses instead of 6.5 billion, but its closeness made it harder to image, not easier. Its accretion disk varies on timescales of minutes, while M87 star varies on timescales of days. The astronomers had to develop new techniques just to keep the target still long enough to capture it. The image showed the same basic structure: a glowing ring of hot plasma swirling around a central darkness. The dark circle in the middle had a name. It was called the black hole shadow, and the size and shape of that shadow could be predicted, with extreme precision, by general relativity. Einstein's century-old equations told the astronomers exactly how large the shadow should appear, given the mass of the black hole and the distance to Earth. The shadow they observed matched the prediction, both for M87 star and for Sagittarius A star. The geometry of spacetime around a supermassive black hole behaves exactly as the theory says it should. There was no deviation, no anomaly, no hint that some other description of gravity might be needed. The bending of light, the warping of space, the cessation of time at the boundary, all of it was confirmed at scales that no laboratory could ever reproduce. But the image showed something else too, something that has only been carefully analyzed in the last 2 years. The bright ring around the shadow is not a simple disk of glowing gas. It is structured. The ring contains within it a series of nested rings, each one made from photons that have orbited the black hole a different number of times before escaping toward our telescopes. Light from the accretion disk that travels directly to us forms the brightest outer ring. Light that grazes the event horizon and is bent halfway around before escaping forms a second, thinner ring just inside the first. Light that orbits the black hole one full time before escaping forms a third, even thinner ring. And so on. Each successive ring is exponentially thinner and dimmer than the one before. The mathematics of how the ring should appear was worked out in detail in 2019 by a team of theorists led by Michael Johnson at the Harvard-Smithsonian Center for Astrophysics. They predicted that the second ring, the photon ring, would have a specific width and a specific brightness, determined entirely by the geometry of spacetime around the black hole. The 2022 Sagittarius A star image was good enough to begin resolving the structure of the photon ring. And what those nested rings reveal is that time itself has structure near a black hole. The photons that form the innermost rings have spent longer inside the gravitational well. They have experienced more time dilation. They left the accretion disk later than the photons that form the outer rings, but they arrived at Earth at the same moment. The image is not a snapshot of a single instant. It is a layered record of multiple moments, all collapsed into one frame. The photograph is a literal cross-section of time. Researchers studying these images are now able to do something extraordinary. They can use the structure of the photon ring to measure gravitational time dilation directly. They can compare the brightness of light that has orbited the black hole 1 time, 2 times, 3 times, and infer the rate at which time was flowing for those photons as they traveled their loops. The data confirms general relativity to a precision that nobody had been able to achieve before. The clocks in the photograph are running exactly as Einstein said they should. And here is the part that has begun to electrify researchers in the field. The structure of the photon ring also encodes information about the black hole that is not visible from any other angle. The ring carries a signature of the geometry deeper inside, near the event horizon itself, in a region where no direct observation is possible. By reading the ring, astronomers may be able to test predictions from quantum gravity, from holography, from the modified models of spacetime that have emerged from the work on emergent gravity. They may be able to determine whether the event horizon is a smooth surface, as general relativity predicts, or whether it has microstructure, as some quantum gravity models suggest. They may, in the next decade, be able to look at the photograph of a black hole and read in the layered rings a direct experimental test of what time actually is. And the answer, if the recent theoretical work is correct, will not be that time is a flowing river. It will be that time is the universe's bookkeeping system. It is how the cosmos keeps track of what information goes where. Near a black hole, the bookkeeping reaches its limit. The ledger fills up. And time, as we experience it, comes to a halt at the boundary where the universe runs out of pages. Let us return to the friend, the one who strapped on a rocket and a clock and began descending toward the event horizon. From your perspective, watching from a safe distance, the friend appeared to slow down, redden, and freeze just above the horizon. The flashes from their beacon grew further apart until they stopped arriving at all. The friend, in your eyes, became a fading impression on the surface of the black hole, a stretched image of a single moment that would persist for as long as you cared to watch. But that is not what happened to the friend. From the friend's perspective, the descent continued. Their clock kept ticking. Their heart kept beating. They crossed the event horizon at a specific moment at a specific reading on their watch, and they crossed it without noticing anything unusual. For a supermassive black hole, the gravitational tidal forces at the horizon are gentle. Sagittarius A star has an event horizon roughly 12 million kilometers across. The difference in gravity between the friend's head and their feet at the moment of crossing would be smaller than what you experience standing on the surface of Earth. There is no jolt, no alarm, no warning. The horizon, from the inside, is invisible. The friend would only know they had crossed it by doing the calculation, by noting their position on their charts and recognizing that they could no longer signal you. Light leaving their flashlight, no matter which direction they pointed it, would no longer reach the outside universe. The geometry of space-time had folded around them. Every direction that used to lead outward now leads deeper in. Inside the event horizon of a black hole, the future and the radial direction switch places. This is not a metaphor. It is a precise mathematical statement about the structure of space-time in that region. Outside the horizon, you can move in any direction in space, but you can only move forward in time. You can walk left, right, up, down, but you cannot walk backward through Tuesday. Time is the dimension you have no choice but to traverse. Inside the horizon, the radial direction, the direction pointing toward the center of the black hole, takes on the role that time previously held. The friend, having crossed the horizon, no longer has any choice about whether to move toward the singularity. The singularity is no longer a place, it is a moment. It is in their future. They cannot avoid it any more than you can avoid tomorrow. They can fire their rocket in any direction. They can accelerate, decelerate, spin, somersault. None of it matters. The singularity is coming, the way midnight is coming for you, regardless of which way you face. This is one of the most disorienting consequences of general relativity. It is also one of the most direct demonstrations that time is not what we ordinarily think it is. Time is not a separate dimension that runs in parallel with space. Time and space are interchangeable under sufficiently extreme conditions. They can rotate into each other the way north and east rotate into each other when you turn around. Near a black hole, the rotation is extreme. Time bends so much that it ceases to be a temporal direction at all and becomes a spatial one. The friend is now falling not just through space, but through what used to be their future. And here is the question that has haunted physicists since the 1960s. What happens at the end of that fall? What is the singularity? The standard answer, derived from general relativity alone, is that the singularity is a point, a single mathematical location where all the mass of the black hole is concentrated, where the curvature of space-time becomes infinite, where the equations cease to produce finite numbers and start producing instead the dreaded result that no calculation should ever produce: infinity. Whenever a physical theory predicts infinity, physicists do not celebrate. They worry. Infinity in a physics equation is almost always a sign that the theory has been pushed beyond the regime where it is valid. The infinity is not telling us about reality. It is telling us about the limits of our model. General relativity predicts a singularity at the center of a black hole because general relativity does not include quantum mechanics. It treats spacetime as a smooth, continuous fabric all the way down to zero scale. But quantum mechanics tells us that nothing in nature is smooth all the way down. At sufficiently small scales, the universe is grainy. It is made of discrete quantum states. There is a smallest meaningful length, called the Planck length, below which the concept of distance probably breaks down entirely. The Planck length is about 10 to the negative 35 meters. That is 1 followed by 35 zeros below a single meter. 100 trillion times smaller than a proton. Long before our friend reaches the mathematical singularity at the center of the black hole, they will have passed into regions where the smoothness of space-time can no longer be assumed. They will have entered a domain where general relativity is no longer adequate to describe what is happening. And in that domain, we suspect the singularity dissolves into something else, something that quantum mechanics governs, something we cannot yet calculate. The honest scientific answer to what happens at the center of a black hole is that nobody knows. The theories required to answer the question, theories that combine quantum mechanics and gravity into a single framework, do not yet exist in finished form. We have candidates. Loop quantum gravity proposes that space-time is made of discrete, interlocking loops at the Planck scale. String theory proposes that the fundamental constituents of reality are tiny vibrating strings that resolve the singularity into a more complex but finite structure. Asymptotic safety models propose that gravity becomes weaker at small scales in a way that prevents infinite curvature from ever developing. Each of these frameworks produces a different prediction about what the inside of a black hole really looks like. But all of them agree on one point: the singularity, as classical general relativity describes it, is probably not real. It is an artifact of using the wrong tools. Reality at the center of a black hole is almost certainly stranger than infinite density. It is almost certainly quantum. And it almost certainly has something to do, once again, with information. Because here is the puzzle that has dominated theoretical physics for the last 50 years. Black holes appear to destroy information. Anything that falls in, the friend, the clock, the rocket, the beacon, every quantum state that define those objects, all of it disappears behind a horizon from which no signal can return. To an outside observer, the information is gone. But quantum mechanics is built on the principle that information is never destroyed. The fundamental equations of quantum theory are reversible. You can run them forward or backward, and they work either way. If you know the state of a system perfectly at one moment, you can in principle calculate its state at any other moment, past or future. Information is conserved at the quantum level the way energy is conserved at the macroscopic level. It cannot be created or destroyed. It can only be moved around. So what happens to the information that falls into a black hole? Stephen Hawking in 1976 argued that the information is simply destroyed. He calculated that the radiation a black hole emits, the Hawking radiation we mentioned earlier, is purely thermal. It contains no information about what fell in. A black hole that swallowed an encyclopedia would emit the same radiation as a black hole that swallowed a chunk of lead of equal mass. Over time, as the black hole slowly evaporates by emitting Hawking radiation, it would shrink and eventually disappear. And the information it had once contained would be gone forever. This was, and is, one of the most disturbing results in theoretical physics. It is called the black hole information paradox. And it places quantum mechanics and general relativity in direct contradiction. One theory says information must be conserved. The other says black holes destroy it. Both theories are confirmed by experiment in their respective domains. They cannot both be completely right, and they cannot both be completely wrong. Something has to give. For decades, the paradox sat unresolved. Then, in 1997, the Argentine physicist Juan Maldacena published a paper that would change the conversation entirely. Maldacena proposed a mathematical equivalence between two seemingly different theories. On one side was a theory of gravity in a four-dimensional spacetime. On the other side was a theory of quantum particles, without gravity, living on the three-dimensional boundary of that spacetime. The two theories, Maldacena argued, were not just similar. They were identical, the same physics described in two different languages. Anything that could be computed in the gravity theory could equivalently be computed in the boundary theory, and vice versa. The two were mirror images. This idea, called the ADS-CFT correspondence, was the most concrete realization of the holographic principle that had ever been proposed. It made the principle precise. It made it calculable. And it had immediate implications for the information paradox. Because the boundary theory was a standard quantum theory in which information is rigorously conserved, if the gravity theory was equivalent to the boundary theory, then information had to be conserved in the gravity theory too, even in the presence of black holes. Hawking had to be wrong. Information cannot be destroyed. In 2004, Hawking himself conceded the point. He stood at a conference in Dublin and announced that he had changed his mind. Information that falls into a black hole, he said, must somehow come back out. The mechanism was still unclear. The mathematics was still incomplete. But the conclusion was now widely accepted. Black holes do not destroy information. They scramble it. They mix it into the radiation they emit in such a complicated way that it is essentially impossible to reconstruct. But in principle, it is all still there. The information about the friend who fell in, every quantum state that defined them, all of it is encoded in the Hawking radiation, hidden in correlations between photons that no telescope could ever resolve, but mathematically present. The friend, in some abstract sense, is not gone. They have been transformed into a signal so complex that no observer in the history of the universe will ever decode it. But the signal exists. the information is conserved. And here is the part that ties back to time. The work on the information paradox, especially in the last decade, has revealed that the conservation of information in a black hole is deeply linked to the geometry of space-time around it. The way information escapes from a black hole through subtle quantum correlations in the radiation it emits is not a separate phenomenon from the way the black hole bends time. They are two aspects of the same underlying structure. Time dilation near a black hole and the eventual recovery of information from Hawking radiation are connected in the mathematics. They are different views of the same fundamental fact. The fact that information is the substrate and space-time is a projection. Researchers like Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and others have spent the last decade developing increasingly precise models of how this connection works. The key insight is something called the entanglement entropy. When two quantum systems are entangled, they share information that cannot be described by considering either system alone. A pair of entangled particles, even if separated by light years, behaves as a single quantum state. Measuring one instantly tells you something about the other. The entanglement is real, measurable, and conserved. In 2006, the physicists Shinsei Ryu and Tadashi Takeyanagi discovered that the entanglement entropy between two regions in a gravitational system is proportional to the area of a certain surface in space-time that separates them. Their result, called the Ryu-Takeyanagi formula, became one of the most influential discoveries in modern theoretical physics. It showed that entanglement, an abstract quantum property, has a direct geometric meaning. The shape of space-time is, in some literal sense, the shape of how information is entangled. This is the picture that has been emerging. Space-time is not a passive backdrop. It is a manifestation of quantum entanglement. Two regions of space that are next to each other because the quantum states inside them are heavily entangled. Two regions that are far apart because their entanglement is weak. Distance, in this view, is a measure of entanglement. And time is a measure of how that entanglement evolves. When you stand on Earth, the quantum states that make up your body are entangled in extremely complicated ways, with the quantum states that make up the planet beneath you, the air around you, the photons streaming in from the sun, the dust drifting through the solar system. Every interaction generates entanglement. Every entanglement contributes to the local geometry. The shape of space-time around you, including the rate at which your clock ticks, is determined by the pattern of those entanglements. Near a black hole, the pattern becomes extreme. Information is being packed into the smallest possible region. The entanglement structure on the event horizon becomes incredibly dense. And the local geometry responds the only way it can. By stretching time, by slowing clocks, by bending the very direction of cause and effect until the horizon becomes a one-way membrane. The slowing of time near a black hole is not a side effect of gravity. It is the visible signature of information piling up against a quantum bottleneck. The clock slows because the universe is running out of capacity to track what is happening fast enough. The horizon is the line where the bookkeeping breaks. Sagittarius A star, at the center of the Milky Way, is one of these bookkeeping breakdowns. Messier 87 star, 55 million light-years away, is another. The universe contains an estimated 100 million stellar mass black holes in our galaxy alone, and roughly 100 billion supermassive black holes across the observable universe. Each of them a region where time has been pulled to its absolute limit. Each of them a place where information has been concentrated to the maximum allowed by physics, and where the local clocks have stopped ticking as a consequence. And then there are the rotating ones. Because everything we have described so far has assumed a perfectly still black hole, a sphere of mass sitting motionless in space. Real black holes are not still. Real black holes spin. And when a black hole spins, time does something even stranger than slow down. Time gets dragged. The discovery that rotating black holes drag space-time around with them was made by the New Zealand mathematician Roy Kerr in 1963. Kerr was working at the University of Texas at Austin. He had been trying to solve Einstein's equations for the case of a rotating mass, the next step beyond Schwarzschild's solution for a static one. The problem had defeated everyone who attempted it for nearly 50 years. The equations were too tangled. multiple researchers had announced approximate solutions that turned out to be wrong. Kerr, working in relative isolation, found an exact solution. He published it as a brief 2-page paper. The solution was so elegant and so unexpected that it took years for the rest of the physics community to verify that it was real. The Kerr metric, as it became known, describes the geometry of space-time around a rotating black hole. And that geometry contains features that the Schwartz solution does not have. The most striking feature is called frame dragging. A rotating black hole literally pulls space-time around with it, the way a spinning ball in a viscous fluid would drag the fluid along with its motion. The dragging extends out beyond the event horizon into a region called the ergosphere. Inside the ergosphere, no observer can remain stationary. No matter how powerful a rocket you have, no matter which direction you fire it, you cannot stop yourself from being carried around the black hole. Space-time itself is rotating beneath you, and you have no choice but to rotate with it. This is not a metaphor. It is a precise prediction of general relativity, and it has been confirmed experimentally. In 2004, NASA launched a satellite called Gravity Probe B, designed specifically to measure frame dragging caused by the rotation of Earth. Earth, like every rotating mass, drags space-time slightly. The effect is tiny, far smaller than the time dilation caused by Earth's gravitational field. But it is real. Gravity Probe B contained 4 gyroscopes, the most precise ever built, polished to within 40 atoms of a perfect sphere. The gyroscopes orbited Earth for nearly 2 years. By the end of the mission, in 2011, the researchers had confirmed that Earth's rotation drags space-time by about 37 milliarc seconds per year. The number matched general relativity's prediction. Frame dragging is real. Now scale that effect up to a rotating black hole, where the central mass is millions of times denser than Earth, where the rotation can be a significant fraction of the speed of light, where the geometry is pushed to extremes the laboratory cannot reach. The frame dragging becomes overwhelming. Space-time around a rapidly rotating black hole twists into a vortex. The ergosphere extends to roughly 50% of the event horizon's radius for a maximally spinning hole. And inside that vortex, time does something that nobody had ever predicted in the Schwarzschild geometry. Time becomes directional in a new sense. There are paths through the spacetime around a rotating black hole that allow energy to be extracted from the rotation itself. The physicist Roger Penrose, working out the consequences of the Kerr solution in 1969, discovered that an object thrown into the ergosphere along a particular trajectory could split in two, with one piece falling into the hole carrying negative energy, and the other piece escaping with more energy than the original object had when it entered. This is now called the Penrose process. It is a way of harvesting rotational energy from a black hole. Roughly 29% of the total mass energy of a maximally rotating black hole is theoretically available to be extracted this way. The energy has to come from somewhere, and it comes from the rotation. Each time the Penrose process is invoked, the black hole spins slightly slower. Slow it down enough times, and the rotation stops entirely. The Kerr black hole becomes a Schwarzschild black hole. The ergosphere disappears. The vortex stills. The point is that rotation does not just decorate a black hole. It contains energy, it contains information, it contains structure. A rotating black hole is a more complex object than a static one. And in the last decade, observations have begun to confirm that real black holes in the universe are almost always rotating, often near the theoretical maximum. The X-ray spectra of accretion disks around stellar mass black holes show characteristic features that depend on the spin rate. Astronomers have measured the spins of dozens of black holes by analyzing those features. The results are consistent. Black holes spin fast. Sagittarius A star, the supermassive black hole at the center of our galaxy, has been measured to be spinning at roughly 60% of its maximum possible rate. M87 star is spinning at roughly 90%. The black hole in the center of the galaxy, NGC 1365, has been measured to be spinning at more than 84% of the speed of light at its event horizon. And the time dilation effects in those rotating black holes are even more extreme than in the static case we have been discussing. Because near a rotating black hole, time is not just slowed by gravity. It is also dragged by the rotation. Two clocks at the same distance from the center, one rotating in the same direction as the hole and one rotating against, will tick at different rates. Time in these systems has a preferred direction. It flows differently depending on which way you are moving. Now, there is one more piece of the puzzle that has come into focus only recently, and it is the piece that has the strongest claim to being a genuine new discovery rather than a consolidation of older theory. It involves what happens to time at the event horizon itself, in the precise mathematical limit where the friend's clock, viewed from outside, comes to a complete halt. For decades, the consensus answer was that the horizon is a perfectly smooth, perfectly geometric surface, and that what happens there is exactly what general relativity predicts. The clock stops, because the space-time has been bent enough to make it stop. End of story. But in 2012, a group of physicists led by Ahmed Almheri, Donald Marolf, Joseph Bolchinski, and James Sully published a paper that challenged the consensus. They argued that combining quantum mechanics with general relativity at the event horizon produces a contradiction. Either information is destroyed, which we have already ruled out, or the horizon is not smooth at all. Instead, they argued, the horizon may be a wall of high-energy quantum effects. A firewall. An infalling observer, instead of crossing a smooth boundary without noticing, would be incinerated at the moment of crossing by a burst of quantum radiation. The friend, in this picture, does not have the experience we described. They do not fall smoothly through an invisible boundary, they hit a wall of fire. The firewall paradox, as it came to be called, has been one of the most contentious debates in theoretical physics over the last decade. Multiple proposed resolutions have come and gone. Some researchers have argued that the firewall is real. Others have argued that the firewall is impossible and that some yet undiscovered principle of quantum gravity must prevent it from forming. Still others have argued that the question itself is meaningless, because the observer outside the black hole and the observer inside the black hole have completely different physical descriptions of reality, and there is no consistent way to compare them. In the last 2 years, a partial resolution has begun to emerge, and it depends, once again, on the precise structure of how time and information are related near the horizon. The resolution is too technical to lay out in full, but its essence can be stated. The event horizon is not, strictly speaking, a single moment in spacetime. It is a region where multiple seemingly contradictory descriptions of reality are all simultaneously valid. From outside, the friend appears to be frozen on the surface forever, their information slowly leaking back into the universe as Hawking radiation. From inside, the friend has passed smoothly through and continues toward the singularity. Both pictures are correct. Both correspond to what an observer would actually measure. The reason they can both be correct, without contradicting each other, is that no observer can ever check both at the same time. The horizon is a place where the universe maintains two consistent histories, neither of which any single observer can fully access. This idea, called complementarity, was first proposed by Leonard Susskind, Larousse Thorlacius, and John Uglum in 1993, but it has gained dramatic new support from the entanglement-based picture of spacetime that has emerged in the last 15 years. The two histories are connected by entanglement. The information about the infalling friend that is encoded in the outside Hawking radiation is the same information that the infalling friend carries with them across the horizon, just expressed in different quantum variables. There is no contradiction. The two pictures are entangled with each other. They are the same physics seen from two angles. And time, in this picture, becomes something almost philosophical. Time near a black hole is not a single number assigned to a single moment. It is a network of relationships between different observers, different reference frames, different ways of slicing reality. The clock on your wrist measures one thread of that network. The clock on a friend falling into a black hole measures another thread. Both threads are real. Both threads are correct. Neither thread is privileged. There is no master clock anywhere in the universe that all the threads have to agree with. The universe does not have a heartbeat. It has a chorus, and each voice in the chorus sings at the rate determined by where it is, how fast it is moving, and how much information is packed around it. The chorus, in the deepest sense, is what time is. Now, with all of this background in place, we can return to the question we started with, and we can answer it more carefully than we did at the beginning. Why does time slow down near a black hole? The textbook answer, gravity bends spacetime, is a description, not an explanation. The deeper answer, the one that has been emerging from a century of work on relativity and quantum information, is something like this. Time is the universe's mechanism for tracking how quantum states evolve. The rate at which time passes in any region of space is determined by the rate at which information is being processed in that region. Where information density is low, time can flow quickly. Where information density is high, time has to slow down to handle the load. A black hole packs the maximum possible information into the smallest possible region. At the event horizon, the universe has reached the limit of what its bookkeeping can handle. The rate of information processing at the horizon, as measured by an outside observer, drops to zero. Time stops, not because gravity has crushed it, but because the universe has run out of pages in its ledger. The friend who falls in does not experience this stop, because from their perspective the ledger has not run out. From their perspective they have plenty of pages. Their local information processing is proceeding normally. Their clock ticks, their heart beats. They cross the horizon and continue toward whatever lies inside. The outside observer and the infalling friend are reading two different pages of the same book, and the book is consistent even though the two pages do not look the same. This is the picture that has come together in the last decade. It is not yet a complete theory of quantum gravity. We do not yet have a final answer to what happens at the singularity. We do not yet know whether the firewall is real, or whether the horizon is truly smooth, or whether some third possibility we have not imagined turns out to be correct. But we know more than we did, and the direction of progress is clear. Time is not fundamental. Time is emergent. Time is what information density looks like from a particular angle. And black holes are the laboratories where the relationship between time and information is being studied in its purest, most extreme form. The recent observations from the Event Horizon Telescope, the gravitational wave detections from LIGO and Virgo, the upcoming missions to study Sagittarius A star at higher resolution, the next generation of space-based interferometers like LISA scheduled to launch in the 2030s, all of these are pushing the precision of our measurements deeper into the regime where the theoretical picture can be directly tested. We are entering a period when the answers to the deepest questions about time may finally be within experimental reach. But before we get there is one more layer of strangeness to unpack. Because the time dilation we have been describing has consequences that extend far beyond the black hole itself. It shapes the entire history of the universe. It determines what we can see from Earth. It governs the structure of every galaxy. And in a way that may be the most disturbing implication of all, it suggests that the universe contains time at multiple speeds simultaneously, all of them real, all of them happening at once, all of them adding up to a cosmos that does not have a single shared present. The universe, in other words, may not have a single now. It may have billions of nows, each one belonging to a different observer, each one as real as the one you are experiencing as you watch this. And the difference between those nows can be measured. The difference between them is the answer to why time slows down near a black hole. The difference between them is what time actually is. Consider what this means in practice. The universe is roughly 13.8 billion years old, as measured by clocks in our local part of space. But that number assumes a particular kind of clock in a particular kind of location. A clock sitting at the center of a galaxy, deeper in the gravitational well of all the surrounding mass, would record a slightly different age. A clock at the edge of a cosmic void, where the gravitational influence is weaker than average, would record yet another. There is no single number that represents the age of the universe in some absolute sense. There are many ages, all of them correct for the clocks that recorded them, all of them differing from each other by amounts that depend on where those clocks were positioned and how they move through cosmic history. The figure of 13.8 billion years is our age, the age recorded by an observer in our gravitational environment, integrated along our particular path through expanding space. It is not the universe's age in any deeper sense. The universe does not have an age. It has many ages. And the question of which age is the right one is, when you press on it, not a question physics knows how to answer. This is not a trivial point. It has practical consequences that have already been measured. In 2023, a team of astronomers led by Geraint Lewis at the University of Sydney published a study in which they used distant quasars, the bright cores of active galaxies billions of light years away, to test whether time itself runs at different rates at different cosmic distances. The prediction from general relativity, combined with the observed expansion of the universe, is that the apparent rate at which time passes for very distant objects, as seen from Earth, should be slowed by a factor equal to 1 plus the redshift of the source. A quasar at redshift 1 should appear to tick at half the rate of a similar quasar nearby. A quasar at redshift 4, observed when the universe was a fifth of its current size, should appear to tick at 1/5 the rate. Earlier work had confirmed this effect for supernovae, where individual events brighten and fade on timescales we can directly compare. But quasars do not have a sharp event we can clock against. They flicker irregularly. They vary in brightness over months and years, but the patterns are stochastic. For decades, attempts to measure the slowed ticking of distant quasars had given inconsistent results. Some studies seemed to show the predicted time dilation. Others seemed to show no dilation at all, leading a few researchers to argue that the standard cosmological model might be wrong in fundamental ways. The 2023 study settled the matter. Using nearly 200 quasars observed over 2 decades, the team showed conclusively that distant quasars do indeed appear to tick more slowly, exactly as general relativity predicts. The universe runs at different speeds in different epochs. The deeper we look into space, the further we look into time, the slower we see things happening. This is not an illusion. It is not a measurement error. It is the literal structure of the cosmos. The fast flickering quasars of the early universe, observed from our position 13 billion light-years away, appear to flicker in slow motion because the universe has expanded enormously since their light began its journey. And that expansion has stretched not just the wavelengths of the light, but the durations between successive arrivals of the photons. Time in the early universe from our perspective is moving in slow motion, and conversely, our time from the perspective of an observer in the early universe would appear sped up. Neither perspective is the truth. Both are. The universe is a structure that allows multiple incompatible time rates to coexist without contradiction. The strangeness of this becomes even more vivid when you consider gravitational wave detections. In September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, recorded its first signal. The signal was a ripple in spacetime caused by 2 black holes colliding 1.3 billion light-years from Earth. The 2 black holes, each about 30 solar masses, had been orbiting each other for billions of years, slowly spiraling closer as they radiated away their energy in the form of gravitational waves. In their final moments, they merged into a single larger black hole, releasing energy equivalent to 3 solar masses entirely in the form of distortions in the fabric of spacetime itself. Those distortions, expanding outward at the speed of light, traveled for 1.3 billion years before passing through Earth and arriving at the LIGO detectors. The signal lasted for less than a second. During that second, the geometry of spacetime around the detectors stretched and compressed by a fraction of the width of a proton, and the most sensitive instruments ever built were able to detect that stretching. Since 2015, LIGO and its European partner Virgo have detected dozens more such mergers. Each one is a record of an event that happened millions or billions of years ago, observed in real time in our laboratories, with extraordinary precision. And each one carries information about the time dilation experienced by the black holes during their final approach. In the last moments before 2 black holes merge, they orbit each other at a significant fraction of the speed of light. The 2 horizons whip around each other in microseconds. The gravitational time dilation in the regions just outside those horizons is so severe that an observer floating nearby would see the rest of the universe rushing past in a blur. Their own time would feel normal. But anything happening outside, anything happening in the distant universe, would be fast-forwarded. And then there is the moment of the merger itself, when the 2 horizons touch and the geometry of spacetime undergoes a transition that has no analog anywhere else in physics. 2 regions of time-stopped space coalesce into one. 2 zones of maximum information density become one larger zone. And the wave that ripples outward from that moment carries with it a record of the geometry's response, an encoded signature of how spacetime rearranged itself when it had no choice but to absorb the combined data of 2 black holes worth of information into a single horizon. Researchers analyzing the waveforms from these mergers have been able to test general relativity to a precision that even Einstein could not have imagined. They have measured the masses and spins of the merging objects. They have confirmed that the final black hole formed by the merger has the predicted relationship between mass, spin, and surface area. They have tested whether the horizon behaves as a smooth surface or shows signs of microstructure. So far, every test has been passed. General relativity continues to be the most accurate physical theory ever constructed. And the time dilation predictions, which are at the heart of how black holes generate their gravitational waves in the first place, have been confirmed to within fractions of a percent. But the gravitational wave detections also raise questions that cannot be answered with current technology. Each merger produces a final black hole that should, in principle, eventually radiate away its mass through Hawking radiation and disappear, returning the information that fell into it to the universe in the process. The timescale for this evaporation is staggering. A solar mass black hole takes roughly 10 to the 67 years to fully evaporate. The supermassive black holes at the centers of galaxies take 10 to the 100 years. These numbers are so large that they exceed the current age of the universe by factors that have no name. The universe is roughly 10 to the 10 years old. A supermassive black hole takes 10 to the 100 years to evaporate. That is the current age of the universe multiplied by itself 10 times, with 90 zeros to spare. By the time even the youngest supermassive black hole evaporates, every star in the observable universe will have died, every galaxy will have dissolved, every proton will have decayed, if proton decay is real, and the cosmos will be a thin soup of stable particles drifting through expanding emptiness. Black holes will be among the last objects in the universe. They will outlast everything else. And when they finally evaporate, they will release back into the cosmos the information they have been hoarding for 100 quintillion times longer than the universe has existed so far. Imagine what time looks like. From the perspective of an observer hovering just outside the event horizon of the last black hole in the universe, they have watched all of cosmic history. They have seen galaxies form, mature, and die. They have seen the cosmic web stretch and dissolve. They have seen the stars wink out one by one. They have seen the universe become dark. They have seen the proton decay scenarios play out. They have seen everything, and they have seen it in fast forward because their own clock has been slowed by gravity to a crawl. From their perspective, the universe has flickered past in moments. From the universe's perspective, the observer has been waiting at the edge of a black hole for timescales that have no analog in any other phenomenon. The two perspectives are both real. The two clocks are both correct. The fact that they disagree by factors of 10 to the 90 is not a paradox. It is a feature of how time actually works. Now you might be wondering, given all of this, how anything in the universe manages to be consistent at all. If time runs at different rates everywhere, if every observer measures different durations, if there is no master clock, how does the universe avoid falling apart into a chaos of incompatible histories? The answer is one of the most beautiful results in physics, and it goes by the name of the light cone structure of spacetime. The light cone of an event is the set of all spacetime points that can be causally connected to that event. Anything that happens within an event's future light cone is something that could, in principle, be influenced by that event. Anything outside the future light cone is causally disconnected. Information cannot travel faster than light, so events outside each other's light cones cannot affect each other. Once you draw the light cones, the universe organizes itself into a structure that is locally consistent, even though it has no global clock. Two observers in different gravitational fields will disagree about how much time has passed between two events. But they will agree on the light cone structure. They will agree on which events could have caused which. They will agree on the order of causes and effects. The disagreement about durations is reconciled by the agreement on causality. The universe maintains its coherence not by enforcing a single clock, but by enforcing a single web of cause and effect. This is why black holes are such a fascinating limit case. At the event horizon, the light cones themselves begin to tilt. Outside the horizon, the light cones point in all directions in space, but always forward in time. As you approach the horizon, the light cones tilt inward. They lean toward the black hole. Inside the horizon, the light cones tilt so far that they no longer contain any direction that points back outward. Every future light cone inside the horizon points toward the singularity. There is no causal path that leads outward. The infalling friend, no matter what they do, no matter what signals they send, no matter what choices they make, has every future event constrained to lie deeper inside the black hole. The light cone has become a funnel. And this is why information cannot escape. It is not that information is being destroyed. It is that the geometry of space-time has been bent so far that no causal path can carry information from inside the horizon to outside. The information remains. It is encoded in the configuration of matter and energy that has fallen in. But the future light cone of every piece of that information is locked inside the black hole. The information cannot reach an external observer through ordinary means. The only way it can come back out is through Hawking radiation, a quantum process that operates at the boundary itself, sneaking information out one particle at a time, encoded in entanglement correlations that no observer with finite resources can ever fully decode. So when we say that time stops at the event horizon, what we mean, more precisely, is that the light cones have tilted so far that the outward direction has been replaced by the past. There is no path through space-time, starting at the horizon, that leads to a future moment outside the black hole. From the outside, this manifests as the friend appearing to freeze. From the inside, it manifests as the friend's future being forced inward. Both descriptions are consequences of the same underlying geometric fact. Both are real. Both are now. Now is, in fact, the most slippery word in this entire conversation. The word now in everyday speech assumes that there is some shared moment that you and everyone else are experiencing together. The now of your kitchen is the same now as the now of New York is the same now as the now of the Andromeda Galaxy. But general relativity tells us that this assumption is wrong. There is no shared now. Two observers in different gravitational environments, or moving relative to each other at high speed, will not agree on which events are simultaneous. Two events that are simultaneous in your frame of reference may be sequential in someone else's frame. There is no way to choose a master frame and declare it to be correct. Every frame is equally valid, and the question of what is happening right now in some distant location does not have a single answer. This was already known from special relativity in 1905. But near a black hole, the effect is amplified to almost grotesque proportions. The now of an observer hovering just outside the event horizon includes virtually the entire future history of the external universe. From their perspective, billions of years can pass outside while they experience moments. The light from distant stars arrives at them blue-shifted into hard radiation. The cosmic microwave background, the faint afterglow of the Big Bang, is heated by the time dilation into a hostile glow. Anything they see in the external universe is happening in cosmic fast-forward. Meanwhile, the now of an observer in flat space, far from any gravitational influence, is entirely different. They see the black hole in distant ages. Light from the infalling friend, red-shifted into oblivion, takes longer and longer to arrive. They watch the universe at its normal pace. Their now matches the now of cosmology. Their clock matches the average rate of the cosmic web. Each observer is correct about their own now. Neither is correct about the others. And the universe somehow holds these incompatible nows together in a single coherent whole. How? Through the light cone structure. Through the rigorous accounting of cause and effect. Through the fact that no observer can ever be in two different reference frames simultaneously, so the contradictions can never be directly experienced. Each observer's now is a slice through a space-time that contains all the other observers' nows as well, just oriented at different angles. The universe is not a sequence of moments. It is a four-dimensional structure in which every moment that ever existed continues to exist, in a sense indefinitely. The block universe view, as philosophers sometimes call it, past, present, and future, are not metaphysically distinct. They're just different slices of the same underlying geometry. The illusion of time flowing comes from the way we, as conscious observers, traverse that geometry along our particular world lines. We experience time as flowing because our memories accumulate in one direction. We remember the past and not the future, but the past does not vanish, and the future does not lack existence. They are simply not where we currently are. This interpretation is controversial. Not every physicist accepts it, There are competing views about whether the flow of time is a real feature of the universe or an artifact of our consciousness. But the mathematics of general relativity, taken at face value, supports the block universe picture. And the mathematics describes the world we observe with extraordinary precision. So when we ask why time slows near a black hole, we are also asking a question about what time is in the first place. And the answer increasingly seems to be that time is not a thing that exists independently and then gets bent by gravity. Time is a property of how the universe organizes itself, and gravity is one of the ways that organization can be locally rearranged. The slowing of clocks near a black hole is not an effect imposed on time from outside. It is a manifestation of what time always was: a coordinate, a bookkeeping device, a way of labeling events along the world lines of observers. The bookkeeping near a black hole becomes extreme, and our intuitions about the steady flow of moments break down. But the breakdown is the truth. The illusion was the steady flow. The reality is that time is whatever the local geometry says it is. Let us now consider a question that has only recently become tractable, and that ties together everything we have discussed so far. Why does the universe contain black holes in the first place? Why has the cosmos arranged itself so that matter can be packed into configurations where time literally stops? The standard answer is that black holes are the natural endpoint of stellar evolution for sufficiently massive stars. When a star runs out of nuclear fuel, the outward pressure that supported it against its own gravity disappears, and the star collapses. For stars below about 3 solar masses of remnant material, the collapse is halted by quantum mechanical pressure, producing white dwarfs or neutron stars. For stars above that threshold, no known pressure is sufficient. The collapse continues indefinitely, and the resulting object passes through the Schwarzschild radius and becomes a black hole. This explanation is correct as far as it goes. But it does not address the deeper question of why the laws of physics permit this outcome. It does not explain why gravity is the only force in nature that has no upper limit on its strength. Electromagnetism saturates. The strong nuclear force has a maximum range. The weak nuclear force is, well, weak. Only gravity, of the 4 fundamental interactions, can be made arbitrarily strong by piling up enough mass. Only gravity has the property that more is always more. And so only gravity is capable of producing the runaway condensation of matter that creates black holes. The reason for this, according to general relativity, is that gravity is not really a force at all. It is geometry. And geometry has no upper bound. You can curve a space as much as you want, given enough mass and energy. There is no resistance from the geometry itself. The fabric does not stiffen at high curvatures. It does not refuse to bend further. It just bends and bends and bends, and eventually it bends so far that it folds itself into a singularity, unless something stops it. And here we return to the question of quantum gravity, because if quantum mechanics is correct, and if there is a smallest meaningful length scale, then the bending of spacetime cannot continue indefinitely. There has to be a point where the curvature becomes so extreme that quantum effects take over and prevent further collapse. What happens at that point is one of the central open questions of theoretical physics. We do not know. We have models, we have hypotheses. We have computer simulations, but we do not have a direct observation, and we may never have one, because the relevant physics happens deep inside an event horizon, in a region we can never see. One leading hypothesis is that the singularity is replaced by a Planck-scale object, a region of finite but extremely high density where space and time themselves break down into more fundamental constituents. In some versions of this hypothesis, the Planck-scale core could even bounce. The infalling matter, having reached the maximum density allowed by quantum gravity, could reverse course and begin to expand outward, producing what some physicists have called a white hole on the other side. The white hole would be the time reverse of a black hole. Where a black hole pulls things in and prevents them from escaping, a white hole would push things out and prevent them from entering. If such an object exists, the matter that fell into a black hole might eventually reappear in some other region of spacetime, possibly in another universe entirely, in a kind of cosmic rebirth. This is speculative. There is no observational evidence for white holes. They may not exist. The mathematics of general relativity allows them as solutions, but mathematical solutions are not always physical reality. Still, the possibility is intriguing, and it suggests that what we call the singularity of a black hole may be more like a transformation than a destruction. Matter and information, instead of being annihilated, may be reorganized at the Planck scale and emitted somewhere else, in some form we cannot currently detect. Another hypothesis, drawn from loop quantum gravity, is that the inside of a black hole contains a kind of recoil, a quantum effect that prevents the collapse from reaching infinite density and instead causes the matter to oscillate in some highly stabilized configuration. The black hole in this picture is not a one-way trip. It is a metastable state, a temporarily frozen lump of matter that will eventually re-emerge as a different kind of object. The timescale for this re-emergence is enormous, larger than the current age of the universe, but in principle finite. A third hypothesis, drawn from string theory, is that black holes are not single objects at all, but are instead enormous collections of microscopic stringy states that account for the black hole's entropy. The event horizon in this picture is not a sharp boundary but a fuzzy halo of vibrating strings. This is called the fuzzball hypothesis, and it has been one of the most actively developed alternatives to the classical black hole picture in recent years. If fuzzballs are real, then the inside of a black hole is not empty. It is filled with the structured quantum states of the strings that make it up, and the information stored in those states is what gets released as Hawking radiation. The singularity disappears entirely in this picture, replaced by a complex but finite quantum structure that extends all the way out to the horizon. We do not yet know which of these hypotheses, if any, is correct. The relevant experimental tests are beyond our reach. But what is clear is that the singularity, as classical general relativity describes it, is almost certainly not the final word. Reality at the heart of a black hole is something else, something quantum, something we have not fully grasped. And whatever that something is, it must be compatible with the time dilation we observe outside. It must be consistent with the entropy and the Hawking radiation and the information conservation. It must mesh with the photograph that the Event Horizon Telescope released, and with the gravitational waves that LIGO detected, and with the GPS satellites that keep your phone synchronized to within a few meters. All of these observations are looking at different facets of the same underlying object, and they all agree on the geometry outside the horizon. The disagreement about what happens inside is purely theoretical, because the observations cannot probe there. For now, there is a possibility, raised in the last few years, that we may not have to look inside a black hole to test these theories. The structure of the photon ring in Event Horizon Telescope images, the precise pattern of how light bends around the horizon, may contain signatures of what happens just below the surface. The polarization of the Hawking radiation, if we could ever detect it, might encode information about whether the horizon is smooth or fuzzy. The waveforms of black hole mergers, measured with the precision that future gravitational wave detectors will achieve, might reveal whether the merging objects had Planck-scale microstructure or were perfectly classical. Each of these is a possible window into the interior, an indirect probe that respects the rule that no causal signal can escape from inside, but that exploits the way the inside subtly influences what happens just outside. The next 2 decades may be the most exciting period in the history of black hole physics. The instruments are ready, the theories are converging. The questions are sharp. We are about to learn things that no human being has ever known before, and if the pattern of the last 100 years is any guide, what we learn is going to be stranger than what we expected. Einstein expected static space-time, and we discovered an expanding cosmos. We expected absolute time, and we discovered relativity. We expected matter to be permanent, and we discovered nuclear physics. At every step, the universe has turned out to be deeper, weirder, and more layered than the previous generation of physicists imagined. The current generation expects, in some sense, that black holes will eventually be understood as something other than infinite singularities. We expect that quantum gravity will reveal a deeper structure beneath the smooth fabric of general relativity. We expect that time, the most familiar and intuitive of our experiences, will turn out to be the most surprising. And so far, Every observation we have made supports those expectations. The pattern is holding, but we have to be ready to be wrong, because the universe has consistently outdone our predictions, and there is no reason to think it will stop now. So let us return one final time to the friend, the volunteer who strapped on a rocket and a clock, and began descending toward a black hole. We left them at the event horizon, falling through smoothly from their own perspective, frozen forever from ours. What happens next? In the most accurate picture we currently have, inside the horizon, the friend continues to fall. The radial direction has become the future. The singularity is a moment ahead of them, not a place below them. The tidal forces, gentle at the horizon of a supermassive black hole, begin to increase as they approach the center. The increase is rapid. By the time the friend is a few hundred kilometers from the geometric singularity, the difference in gravity between their head and their feet has become significant. They begin to feel themselves stretched. The stretching grows. Within seconds, by their own clock, the tidal forces become lethal. The friend, made of atoms held together by electromagnetic forces that are no match for the extreme gravitational gradients, comes apart. Their cells rupture. Their molecules break. Their atoms scatter. By the time they reach the Planck scale region, where quantum gravity takes over, they are no longer recognizable as the friend who began the journey. They are a stream of disassembled matter, falling along the inexorable geometric path toward whatever the interior of the black hole actually is. From outside, none of this is visible. From outside, the friend's image is still frozen on the horizon, slowly fading as the last photons climb out of the gravitational well. The two pictures, the friend's experience and the outside observers, are reconciled by the rule that no information can leak between them. They are entangled. They are connected by quantum correlations in the Hawking radiation. They are two consistent descriptions of the same physical situation. Neither is more real than the other. And the time scale on which the two pictures will eventually reconverge, when the black hole has fully evaporated and the information has been returned to the universe, is so long that it has no meaningful analog in human experience. It is a duration that exceeds the age of the universe by factors that exceed the number of atoms in the observable cosmos, but it is finite. It is the time scale on which the answer to what happened to the friend will become, in principle, recoverable. The friend, in some sense, is not lost. They have just been temporarily encrypted by the strongest cryptographic process the universe has at its disposal. The encryption will eventually decay. The information will eventually leak back out. And on timescales no observer will ever survive to witness, the friend's pattern, in some abstract sense, will be released back into the cosmos. This is what time slowing down near a black hole really means. It is not that clocks tick more slowly because of some local effect. It is that the universe is taking a longer route to process information through that region. The clocks measure the route. The route bends, twists, and folds back on itself near the horizon. The friend has taken a path through space-time that, from the universe's bookkeeping perspective, is enormously longer than the path their image appears to be taking from your viewpoint. The two paths look different. Both paths are real. And the geometry that contains them both is what physicists are increasingly coming to believe is constructed out of quantum information itself. There is a sentence that physicists sometimes say to each other, almost as a joke, but it captures the deepest truth of this entire subject. Time exists so that everything does not happen at once. It is offered as a quip, but the more you sit with it, the less like a joke it becomes. Time, in this view, is the universe's way of imposing order on what would otherwise be an undifferentiated chaos of every possible event happening simultaneously. Time spreads events out. It gives causes a chance to precede effects. It allows information to flow from one configuration to another in an orderly way. And near a black hole, where the geometry of spacetime has been pushed to its absolute limit, the spreading out function of time is overwhelmed. Information piles up. Events accumulate at the horizon faster than the universe can organize them into a coherent sequence. The clocks slow because the bookkeeping is straining. Push the bookkeeping past its limit, and the result is what we observe. A region where time, as we experience it, has been brought to a halt. This is the picture that has emerged. It is not finished. The full theory of quantum gravity that would make all of these ideas rigorous is still in development. Researchers around the world, from Princeton to CERN to the Perimeter Institute to dozens of universities and institutes I cannot name in a single breath, are working on the pieces. They are computing entanglement entropies, building lattice models of quantum spacetime, analyzing gravitational wave signatures, and refining the photographs of black hole shadows. Each year, the picture becomes a little clearer. Each year, the strangeness becomes a little more precise. And the central insight, the one that has only fully crystallized in the last decade, is that the question of why time slows down near a black hole is not really a question about black holes. It is a question about what time is, anywhere, everywhere, in any region of the universe. The answer for the black hole is the same answer that applies to your kitchen, to the surface of the sun, to the cosmic microwave background, to every point in spacetime that has ever existed. Time is information. Time is the rate at which the universe processes its own quantum state. Time, in regions of low gravity and low energy density, runs fast because the information processing is sparse and rapid. Time, in regions of extreme gravity and extreme information density, runs slow because the processing is bottlenecked. The relationship between time and gravity, which Einstein discovered a century ago, is just the macroscopic shadow of a deeper relationship between time and information that is only now coming into focus. Now here is the practical part of this story, the part that may surprise you. You experience this strangeness every day, whether you realize it or not. Every smartphone in your pocket contains a chip that talks to the Global Positioning System, a constellation of satellites orbiting roughly 20,000 kilometers above Earth's surface. The satellites carry atomic clocks. The clocks broadcast precise time signals. Your phone receives signals from at least 4 satellites simultaneously, measures the tiny differences in their arrival times, and uses those differences to triangulate your position. The system works to within a few meters of accuracy. But here is the catch. The satellites are orbiting in a weaker gravitational field than the surface of Earth. Their clocks, by general relativity, run faster than clocks on the ground by about 45 microseconds per day. They are also moving at high speed relative to the surface, which, by special relativity, makes their clocks run slower by about 7 microseconds per day. The net effect is that the satellite clocks tick about 38 microseconds per day faster than clocks on Earth. If the engineers who designed GPS had not accounted for this, the system would accumulate errors of several kilometers per day. Within a single afternoon, your phone would no longer know where you are. The entire GPS infrastructure works only because the engineers explicitly programmed in corrections derived from Einstein's equations. Every time you use a navigation app, you are relying on the fact that time slows down in gravitational fields. It is a daily, mundane confirmation of the same physics that governs the event horizons of black holes. The same equations that explain why the friend's clock froze at the boundary of Sagittarius A star explain why your phone can find a coffee shop. There is a continuum here, from the everyday to the extreme. Gravitational time dilation is not exotic physics that only matters near black holes. It is part of the structure of every gravitational field everywhere. The Earth dilates time by tiny amounts. The Sun dilates it by more. A neutron star, if you happen to be standing nearby, would dilate it by a significant fraction. A black hole dilates it to the maximum. The effect is the same effect throughout. The difference is only in degree. And this should change how you think about the place you occupy in the universe. You are not standing in a static present. You are sitting at a particular depth, in a gravitational well, on a planet that is orbiting a star that is orbiting a galactic center that contains a 4 million solar mass black hole at its heart. Your clock is being affected by all of these masses, all the time. The rate at which you are aging, the rate at which your thoughts are forming, the rate at which the light from this video is reaching your eyes, all of it is being subtly modulated by the geometry of the space-time you inhabit. You are not separate from the cosmos. You are made of the same time that bends around stars and stops at the edge of black holes. The difference between you and the friend who fell in is only a matter of degree. And here is where this whole story becomes, in a strange way, comforting. We have been talking for a long time about how time slows down, freezes, and stops near a black hole. We have been describing limits, extremes, breakdowns. But the same physics tells us something else. Time, here in this room, where you are watching this, is running at the normal rate for this particular location in the universe. Your clock and the cosmic web are roughly in sync. You are in a relatively low-density region of space-time, far from any black hole, far from any intense gravitational source. Drifting along with the cosmic flow at the rate that the universe has determined is right for an observer in your circumstances. You are, in a real sense, experiencing the universe at its standard pace. The deep past sees you in fast forward, just as you see it in slow motion. The deep future, if any observer exists there, will see your moment as a blur. But for you, right now, the moment is fully extended. You have it. It is yours to live through. And it is happening at exactly the rate that the geometry permits. There is a passage in the writings of the cosmologist Sean Carroll that captures this well. Carroll has spent much of his career thinking about the nature of time, and he has argued that the most remarkable thing about our place in the cosmos is not how strange it is, but how livable it is. We exist in a region and an era when the laws of physics, including the laws governing time, allow conscious beings to form, to act, to remember, to anticipate. We are not perched at the edge of an event horizon, watching the universe whip past in unimaginable speed. We are not buried at the heart of a singularity, where time itself breaks down. We are in the middle, in a clearing, in a place where the cosmic clock ticks at a rate compatible with biological life and reflective thought. That is rare, that is precious. The vast majority of the universe is not like this. Most of the cosmos is too hot, too cold, too dense, or too empty for anything like a clock or a thinker to exist. We have stumbled into one of the rare habitable pockets of a much larger, much stranger geometric structure. And from inside this pocket, we have managed to figure out, to a remarkable degree of accuracy, what the rest of the structure looks like. We have inferred the existence of black holes. We have photographed them. We have detected the gravitational waves from their collisions. We have derived the equations that govern the behavior of time at scales we will never visit. We have, through pure mathematics and careful observation, mapped the geometry of regions of spacetime that no human will ever physically experience. This is, when you really sit with it, an astonishing achievement. The cosmos contains regions where time stops. We know this, we have measured it. And we know it from within a small, biological, embodied, finite vantage point on a single planet, around a single star, in a single galaxy, in an observable universe full of billions of others. The same brains that evolved to track prey on African savannas have managed to deduce the structure of an event horizon. The same hands that crafted stone tools 80,000 years ago have built telescopes that can image the photon ring of a supermassive black hole 55 million light-years away. The same consciousness that flickers behind your eyes as you watch this is, in the abstract, the same consciousness that figured out general relativity. We are small, but we are extraordinary. The universe contains us, and we contain a description of the universe. There is a feedback loop here that has no obvious analog in nature. Atoms, given enough time and the right conditions, organize themselves into structures that can model how atoms work. Spacetime, given enough complexity, produces patches of itself capable of mapping its own geometry. Time, given enough information density, becomes something that can study itself. We are not separate from the physics we have been describing. We are the physics looking back at itself. And so when we ask why time slows down near a black hole, we are, in a sense, asking why we exist. Because the same laws that produce time dilation near event horizons produce the gentle, livable, temporal flow that allows life and thought to develop. The two are different settings of the same dial. Crank it one way, and you get a universe in which clocks freeze at horizons and observers are forever sundered from each other. Crank it the other way, and you get a universe in which the cosmos is dispersed too thinly for structure to form, where time runs uniformly and meaninglessly without anything to mark its passage. We are at the setting in the middle. The setting where time has enough variation to be interesting, but not so much that we are torn apart by tidal forces. The setting where information has enough density to be processed into thoughts, but not so much that the local geometry collapses. The setting that produces, against the long odds of cosmic chance, the conditions for a being to ask why time slows near a black hole, and to be capable of working out the answer. The answer, after all of this, is something like this. Time slows near a black hole because time is information density, and a black hole is the universe at maximum density. The equations of general relativity describe how this works at large scales. The mathematics of quantum gravity, still being assembled, describes how it works at small ones. The two descriptions are converging on a single picture in which space-time emerges from quantum entanglement, and the rate of time emerges from the rate at which entanglement is generated and processed. The clock on your wrist measures the local rate. The clock at a black hole's horizon measures the maximum. And the difference between the two clocks is not just a curiosity. It is the geometry of how the universe is built. There is one more thought to leave you with. We have been describing time as if it were something the universe does, a process that the cosmos imposes on its contents. But there is another way to look at it. Time is also something that we, as conscious observers, perform. Without observers, the question of whether time is flowing has no obvious meaning. A block universe, considered all at once, does not flow. It just exists. The sensation of flow, the feeling of one moment giving way to the next, the experience of nows accumulating and pasts receding, is something that happens in the minds of conscious beings as we traverse our world lines. The universe contains the geometry. We contribute the flow. This is, again, a contested interpretation. Not everyone agrees. But it is consistent with the mathematics, and it offers a particular kind of consolation. Even if the universe is in some sense already complete, with every moment laid out from beginning to end in a fixed geometric structure, our experience of those moments is not predetermined in the way that the geometry is. We live the moments, we feel the flow, we participate in the unfolding even if the unfolding has, from some God's eye view, already unfolded. This means that even when we contemplate the strangeness of time near a black hole, even when we imagine a friend frozen forever on a horizon while their other self has long since reached the singularity, even when we confront the relativity of simultaneity and the absence of a master clock, there is still something irreducibly real about the moment you are in right now. This sentence, the one you are listening to, is happening at its own rate, in its own present, at its own location in the geometry of the cosmos. It is yours. It belongs to you in a way that no equation can take away. The universe may contain many nows, but yours is the one you have access to. The others belong to other observers. And the very fact that you can hold this moment, while also understanding that other moments exist for other observers, and that there is no preferred ordering between them, is what consciousness inside a relativistic universe looks like. It is what we are. It is the strange and wonderful condition of being a thinker inside spacetime. The Event Horizon Telescope's photographs of black hole shadows are, in this sense, photographs of our own situation. They show the cosmic limit case of a phenomenon that touches every clock in the universe. They show what happens when the same physics that gently slows the watch on your wrist by a few nanoseconds per year is pushed to its absolute extreme. They show time itself, drawn in the geometry of a single suspended ring of light. When you look at those images, you are looking at the universe's most direct visual statement about what time is. And what it is, increasingly, looks like a question that has no simple answer. Time is what clocks measure. Time is the dimension that ticks. Time is the rate at which information flows. Time is the local emergent property of an underlying quantum substrate. Time is the universe's way of preventing everything from happening at once. Time is the parameter along which conscious observers experience the unfolding of geometry. All of these definitions are partly correct. None of them is fully correct. And in the regions of spacetime where time has been bent the furthest, where the geometry has been pushed to its limit and the equations begin to break down, the search for a complete definition is still ongoing. We are not done. We may never be done. But we have come further than anyone has any right to expect. From Newton's equable river to Einstein's curved spacetime to Hawking's evaporating horizons to the entanglement-based pictures of the last decade, the human understanding of time has expanded immeasurably. And every expansion has revealed that the universe is stranger, deeper, and more interconnected than the previous picture suggested. Time slows near a black hole because the geometry bends. The geometry bends because mass curves spacetime. Mass curves spacetime because spacetime is built out of quantum information, and mass is what concentrated information looks like from a distance. And quantum information is, as far as we can currently tell, the substrate from which everything else is constructed. The atoms that make you. The photons that show you the world. The galaxies that fill the sky. The black holes that anchor the centers of galaxies. The friend who fell in, and the observer who watched, and the equations that describe both. All of it, in the deepest analysis, is information processed by the universe at the rate that its local geometry permits. Time is the rate. The rate is the bookkeeping. And the bookkeeping, at the edge of a black hole, slows to a halt. Somewhere, right now, light is orbiting a black hole. Photons that left the surface of an accretion disk are looping around the event horizon, taking longer and longer paths before escaping toward telescopes on Earth or on distant worlds. Each photon carries with it a record of the moment it began. Each photon, by the time it reaches an observer, has experienced a different amount of time than its companions, depending on how many loops it took. Each photon is a tiny clock that has been running at a different rate from the others. And when those photons arrive at the same instant at the same telescope, they bring with them a memory of an event that, from the universe's perspective, never had a single timestamp. The event happened at many times, simultaneously, and the photograph collapses them into one frame. This is, finally, the answer to what time is. Time is the chorus. Time is the network of relationships between observers. Time is the structure that holds together the many threads of experience that the universe contains. It is not a single thread, it is the weave. And black holes are the places where the weave is pulled tight, where the threads converge, where the geometry of the cosmos shows you, more clearly than anywhere else, the underlying structure of how it all fits together. We started this journey by asking why time slows down near a black hole. We have ended by understanding that the question contains, within itself, the question of what time is, what the universe is, and what we are. The slowing of clocks is not an isolated phenomenon, it is the visible signature of a deeper truth. Time is information. Information is the substrate. We are the patterns. And the patterns flow, locally, at the rate that the geometry permits. So the next time you look up at the night sky, knowing that somewhere among the stars there are dark patches where time has been pulled to a halt, remember that you are part of the same fabric. The same physics. The same vast geometric structure that contains everything from the photon ring of Sagittarius A star to the watch on your wrist to the rate at which your thoughts are forming as you take in these words. You are not separate from the universe that contains black holes. You are made of the same time that bends around them. And the fact that you can hold both of these truths in mind at once, the fact that you can grasp time dilation at the event horizon while also being a small biological observer with a finite span of moments to live through, is what makes you remarkable. You are the universe noticing that it slows down near a black hole. You are the universe, briefly, knowing itself. The clocks at the edge of Sagittarius A star may have stopped, from our perspective. But yours has not. It is still ticking. Each second still belongs to you. Each thought still has time to form. And in a universe full of regions where time has been compressed, stretched, frozen, and reversed, the gentle, steady flow of your own moment is, in its own way, a kind of miracle. The universe could have been built so that nowhere in it allowed for consciousness to settle into a stable rhythm. It could have been all extremes, all frozen horizons and runaway expansions, with no clearing in the middle where a clock could tick at a livable pace. But that is not the universe we got. We got the one with the clearing. We got the one with the gentle rate. And in that clearing, against the most extraordinary odds, beings like us have managed to figure out why time slows down near a black hole. We have managed to confirm it with photographs and gravitational wave signals and atomic clock measurements that span continents. We have managed to extract from the mathematics of general relativity an idea so strange that Einstein himself initially doubted it, a working theory of how the cosmos handles its temporal bookkeeping. And we have managed to do all of this while existing as transient patterns of matter and energy whose own time will eventually run out. That is the deepest mystery of all, not why time slows near a black hole. We now have a working answer to that. The deepest mystery is why a configuration of atoms ever became capable of asking the question in the first place. And whatever the answer to that is, it is happening right now, in you. If you enjoyed this journey into the deepest physics of time and the strange behavior of clocks at the edge of a black hole, please leave a like, And consider subscribing to Hidden Beyond Stars. We make these nighttime documentaries to share the wonder of the cosmos with anyone who wants to think about big questions in the quiet hours. Tell us in the comments what surprised you the most. Was it the photograph of the photon ring, the friend who falls smoothly through a horizon that frozen onlookers cannot watch them cross, the realization that GPS satellites depend on Einstein's equations every day, or the deeper idea that time itself may be made of information? And tell us what you would like us to explore next. There are corners of physics darker and stranger than this one, and there are questions we have only begun to ask. We will see you in the next investigation. Take a breath. Hold the moment. The universe is bending around you, even now, and your time, briefly, is your own.